Hello there, Algebras. Welcome to your Chapter 11 Lesson 4 notes, all about applying graphing quadratic functions to some real-life scenarios. So today what we're going to look at is mostly like throwing stuff and stuff jumping out of the water and dropping things. Because gravity changes at a quadratic rate, everything that we throw up comes down in the form of a parabola. So this is pretty cool that this is how it works. What this means for us is, why is a projectile such as tossing a ball, launching a rocket, or diving from a platform a quadratic function? Because gravity is quadratic. That's why. Also, by the way, something goes up, 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 and then hits a maximum point and comes down, down, down. And so the change over time, even if it's straight up and straight down, if you use X as your time and look at that over a time period, it looks like an actual parabolic movement, right? So even if that is the case, that it's just boom, oh, straight down right there, it still looks like a parabola when we do that over time. So actually, what you probably just picked up on too is these are negative x squareds every time, because we're going up and hitting a maximum and then coming back down. So, okay, what's this going to look like? X coordinates are going to be our time, Y coordinates are going to be our height. And time and height might be measured in different types of things. You know, time could be seconds, minutes, hours, days, if it needed to be. Height, inches, feet, meters, centimeters, you know, it could be yards even. Like, it depends on the particular thing that we're looking at. That means that your vertex or turning point is going to represent the maximum, or the amount of time it took to hit the maximum height. That means as we graph, the C value is going to indicate how high we started from. When 0 as our X value for time, that's when we're starting our measurements from. So where did we start at 0 time measured yet? Let's look at a few examples of this happening. You know, sometimes we'll replace the X with a T. So sometimes that will happen, like in exercise 1. We're replacing the X value with a T. It's still going to be plugged into our graphing calculator the same way. Okay, so in exercise 1, S of t is equal to negative 16t squared plus 64t plus 80, okay? It's some sort of projectile. Let's just call it, we're throwing a ball, okay? Let's just call it that. We're throwing a ball up in the air, and this equation, this quadratic equation, models that ball's movement over time in seconds. So the reason I know it's height in feet and time in seconds is that is what's labeled on the graph that's given to me. Now let's consider what would be an appropriate domain and table for talking about this, okay? So let's grab our graphing calculator. You clear your RAM before you start. Second, and the plus sign, 712 clears off your RAM, which I did already have RAM cleared, but it's nice to demonstrate it. Then let's turn on the graph table piece so we can see the graph and the table at the same time and work with them together. Okay, so let's press mode, arrow all the way down to full, arrow right to graph table, and press enter. We'll turn on graph tables so we can see them together. Now let's press y equals, and let's plug in our function equation. Negative 16, so it's the little negative under 3, and this is the only time we press that when typing in a function, is if your function starts off negative. That, by the way, tells me this is a frowny face parabola, right? So we know that this is frowny face because it starts off with a negative x squared plus 64x. So remember, I'm replacing x with t with x in my graphing calculator because I only have an x to use to type, and then my plus 80. And so when I press graph to see both the table and the graph at the same time, we can see that, well, wait a minute, since the y-intercept is 0, 80, so my y-intercept is 0, 80. It's always 0 and whatever my c value is in my function. So since that is the case, that is certainly not going to fit on a 10 by 10 grid. So I am seeing very little of the points on this parabola. But also, I know there's some stuff back here negatively, but am I going to think about before we measured the time? That's what the negative x's would be. Am I going to think about negative x values, negative time? No, I'm not. So because I'm not going to think about that, an appropriate interval of x values or t values for time to think about starts at 0 and ends wherever my ground is. Because, wait a minute, these y values are height above the ground. Am I going to consider negative y values? No. So my ending t value is going to be 5. So, of course, x and t are interchangeable in this particular case, again, because the graphing calculator only has x as our variable input option. But our function that we actually are using on our paper has a t in it. So now what we can see on our table is that we are only able to write down a starting x value and a matching y value at 80 feet in the air. What does this mean? It means that whatever we threw, we started out 80 feet high when we threw it. Then after 1 second, that object was 128 feet high. After 2 seconds, that object was 144 feet high. After 3 seconds, it was then 128 feet high. Oh, we spotted our max back here. Took 2 seconds to get to its maximum height. Then we've got 3, 128. We've got 4, 80. Oh, so we're back to the platform that we started on. And then, boom, 5, 0. There's the ground. There's the ground. Okay. So before I even graph this, I can answer some of these questions. How high did the object reach? What was the maximum height? 144 feet. How long did it take to reach that height? 2 seconds. How long was the object in the air? It was in the air from 0 to 5 seconds. So we're going to say 5 total seconds before it touched the ground. Okay. Now we need to figure out how to graph this particular thing using the graph that's provided for us. So of course, time in seconds is going to be our x-axis, and it's already labeled as such. I like to stretch things like this out a little ways. So since I have plenty of room, I'm going to skip count. I'm going to start with 0 seconds here, but I'm going to skip 2 and then put 1 second. And I'm going to skip 2 and then put 2 seconds. So I can spread this out just a little bit space-wise. Okay, it's not going to be crammed all in. Now, height in feet, since my maximum height is 144 feet, I need to count how many lines I have that I'm trying to fit this on. And then I can go from there. And so, of course, 0 feet, 0 height in feet is going to be right here. Okay, we're not doing negatives in either direction. There's not negative time. There's not going to be negative height. Now, let's see how many lines we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have 25 lines to deal with. If we press second in mode, we're back to our home screen. And we can take 144 divided by 25 lines and see what we come up with. Okay, so we can't go by twos. Can't go by 4s. We could go by 6s. But if we kind of look at these values, all these values are evenly divisible by 8. So I'm going to go by 8s on my table, and I will have plenty of room to fit everything. So if you go 8, 16, 24, 32, 40, okay, then 48, 56, 64, 72, 80, that's where my platform is, 88, 96, where am I? Plus 8, so 104, 112, and 120. And, oh, look, this one is going to be 128, which is one of our values. So we've got 80 on there. We've got 128 on there. Then let's see, plus 8, we've got 136. Okay, and then we get to, where am I? Oh, 144. Nice. Okay, there's my max, 144. I'm going to put that on there. And let me put 128 on here because those are actual values that we get to. And I'll just kind of head up a little bit further to get to my 160. There we go. Just again, so that I have like enough space that I'm really seeing what's happening here. Okay, so 0 and 80, 0, 80. There's my y-intercept. That's the height of the platform I started on. After 1 second, we were up to 128 feet in the air. 2 seconds, we hit our max at 144. At 3 seconds, we were back to 128. At 4 seconds, we were back to the platform at 80 feet in the air. And at 5 seconds, we were here at the ground. All right, and now we'll connect. And everything we put on the graph, we put a label on. This is S of t equals negative 16t squared plus 64t plus 80. Okay, you can see visually what questions we already answered over here. But this is what we're looking at doing today. Graphing these functions, but based on some real life scenario of some kind. Now that was a nice one. I like that one. Very nice and easy numbers to deal with. Easy as far as fitting on the graph. Okay, and I stretched it out a little bit to fit things. Let's now look at the dolphin question. So the dolphin jump. And it looks like I added a couple things to something we already had going on in the dolphin jump. The height and feet of a dolphin as it jumps out of the water at an aquarium show can be modeled by the function f of x equals negative 16x squared plus 32x, where x is the time in seconds after it exits the water. Graph this function, find the dolphin's maximum height and the time it takes to reach this height. Then find how long the dolphin is in the air. Okay, sounds great. Let's go to y equals. Let's clear this out and let's retype the new function in. So negative 16x squared plus 32x. Oh, there isn't a c value, so I know my y-intercept is 0, 0. So when I start recording, the dolphin is still in the water, right? So when I start time, dolphin's still in the water, and then it'll jump out and come back down to the water. So 0 for my y values is going to be the water, the ground level of the water level, I suppose we would say. And whatever time I hit my max, that's going to be my amount of time that the dolphin took to reach its maximum height. That's going to answer that question. And whatever my max is, that's my highest y value. So if I press second and graph, oh my God. There's not a lot on this table, is there? Well, why don't we look at some half seconds? Because I have like nothing to go on here. So let's go to second and window. Stay at 0, of course, for my start, but let's look at 0.5 of seconds so we can see some sort of middling going on here. And Okay, at least now we can see at half a second, the dolphin is already 12 feet in the air. This is a tall jumping dolphin. All right, here's where my table is going to go. I'll just put my table horizontally. And I will include these half points. So 0, 0, of course, no time, we're still at the water. That's going to be right here. Let me just kind of sketch in my half seconds. So this will be 0.5. This is 1.5. At 0.5 seconds, the dolphin is 12 feet high. At 1 second, the dolphin hits its maximum height of 16 feet. And then at 1.5, we're back down to 12 feet high. And at 2 seconds, we are back hitting the water. So from here to here is all we are out of the water, those 2 seconds. At 1 second, we're all the way up to 16 feet in the air. And then at our half seconds is where we get to 12 feet in the air. So at those half seconds. That's what the dolphin jump looks like. So this is the dolphin jump. Boom, 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 and boom. That's what the dolphin jump out of the water looks like. Our maximum height, 16 feet. Time to take to reach that, 1 second. Whew. Time in the air total, 2 seconds. We're really only out of the water for 2 seconds. And now, this one I added. Describe what you know about the interval for x from reading the problem. Well, x describes the amount of time the dolphin is out of the water. In questions like this, it's important to note that what is happening in the problem needs to be directly addressed by what your x and y are measuring. So you need to take context from your reading and be able to describe what your x's are talking about. They are talking about the amount of time that your dolphin is out of the water. What are the y's talking about? They are talking about how high above the water level the dolphin reaches. So you need to be able to describe what your variables are representing in these real life scenarios. So that's why, while it's a little lengthy word-wise, it's important to read the problem maybe even a few times so we know what each variable really truly represents. Now, here's an interesting one where we are just using the table of points. We aren't doing anything else but looking at the table of points. So I'm not going to graph what this looks like. So let's go to y equals. Let's clear out what we have in there and let's put this next function in to start thinking about, just based on the table, what's happening. So the height and feet of a toy rocket is modeled by the function y equals negative 16t squared plus 128t, where t is the time in seconds after it is launched. Okay, good description. Negative 16x squared in place of t plus 128x, again in place of t because we only have an x as our option. So x is going to be modeling our time for us. Let me get a table ready. I made a lot of room. I don't even know if there's a lot of room yet. Second and graph gets me my table of points. Oh, I was still going by 0.5s. Let's see, does it look like I really need to be going by 0.5s here? Probably not. So you know what? Let's just press second in window. Let's keep our table start at 0, but change our table to be going by 1s. So we went back from 0.5s to 1s. Now press second in graph. I think that's plenty of space to see this, right? So 0, 0, of course, starts this off. Then you've got 1 and you're up to 112 feet. So this is that rocket, time in seconds. And t is the height in feet for my rocket. 2 seconds, we're at 192. 3 seconds. Oh, good rocket. We are at 240. 4 seconds, we get up to 256. 5 seconds is back to 240. Oh, we found our axis of symmetry and vertex. Okay, so we know that the ground is my y value of 0 and the start of time 0 for my x value. Now let's see, I'll keep going. We have 6 and we're back down to 192, and we have 7 and we're back down to 112. We're approaching the ground, and at 8 seconds, boom, ground again. So in this case, the roots actually describe when I am on the ground for this rocket. The maximum height of the rocket is 256 feet. How long does it take to get there? X value of 4 seconds. The amount of time the rocket is in the air, from 0 to 8, so 8 seconds. Okay? Let's see how they've asked this on the Regents before. It's nice to have some context, but it's even better to know what is someone else going to require of me as far as this goes. So the path of a rocket is modeled by the function h of t equals negative 4.9 t squared plus 49t, where h is the height in meters above the ground and t is the time in seconds. Okay, so there we go. H of t, that's my y values, and t, my time in seconds, that's going to be my x values. Okay, cool. We want to sketch this on the graph provided. All right, well, let me at least get this into my graphing calculator. Y equals negative 4.9 x squared, is that a t, plus 49x, negative 4.9 t squared plus 49t. Yep, there you go. That replaces those. And now we can press graph to see this. Oh, we're not seeing a whole heck of a lot. Oh, okay, we've got a lot of these like points going on, these integer points going on. Press second and graph to see my table, be on my table, starting at 0, 0, ending at 10, 0. This gives you exactly what you need as far as that gives you your scales on each side. So you know what I'm going to do? I am going to get my table of points on here. Okay, so 0, 0. And then let's see. Let's arrow up and down. So now we've got 1. I just want to go to this side. Okay, just making sure that it is actually 44.1. 2 seconds. Let's arrow down again. Okay, 78.4. 3 seconds. 102.9. 4 seconds. 117.6. 5 seconds. 122.5. 6 seconds. Oh, look at this. Well, we found our axis of symmetry and vertex. So it took 5 seconds to get to my maximum height of 122.5 feet in the air. Okay, 102.9, 8 seconds, 78.4, 9 seconds, 44.1, and 10 seconds, we're back at 0. Okay, so they're back at the ground, starting off the ground. So the few things that I do know about my graph just from my table of points. All right, let's get these on here. So 0, 0, and 10, 0 are my only integer points. At 5 seconds, I'm going to go all the way up to 122.5. So here's 125. So let's see what we go by. 5, 10, 15, 20, 25. So these are going by 5s. See that? So at 120 and 5, we're right here. 120 and 5, so 122.5 right about here. And then let's see, let's get some points on each side. 117.6. So here's 115. So 117.6. Okay, I did that right. There we go. And 102.9. Okay, so at 3 seconds, 102.9. And that's also over here at 7 seconds. Then we're at 78.4, and that's 2 seconds and 8 seconds. So 75, and then this is 80, so right about here. It is sketchy, right? And it does say sketch the graph, so it's not exact points. Pretty tough when there's only 2 integer points on the whole thing. Then you're at 144.1 and 944.1, so there's 50. This one's 45, so 44.1 right about here. And right about here. And then you're down to 0, 0, and 10, 0. So now connect. This is curved, so we are not using a straight edge to do this connection. We are doing our best, of course, to make this look parabola-ish. There we have it. Nice job. We can visually see that axis of symmetry and vertex right here, that maximum. So our axis of symmetry is at x equals 5 for our equation of our axis of symmetry. We can definitely see that. I'm not going to put arrows on the end because obviously the rocket starts here and ends here, so it's not like we need arrows continuing to go on what's going on here. I am going to model the equation on here just because I can't see it on my paper right now based on what else I need to see, so I'll put that right there for you. And of course, here's the ground at the roots. So this is kind of nice. State the vertex of this function. Okay, that vertex would be 5, 122.5. And explain what the vertex means in the context of the situation. Great, we can do that pretty easily. Okay, the context of this situation was that we had a rocket who had h is the height in meters above the ground, and t is the time in seconds above the ground. So sorry if I said feet at all. In there it was meters. Explain what the vertex means. At 5 seconds, comma, the rocket hits its maximum height of 122.5 meters above the ground. Period. That exactly describes what the vertex is saying when we have a vertex in context for our problem. Okay, a former Regents question. Good to look at. Very good to look at for exercise 4. This is the type of stuff we're going to be looking at in 11-4 homework. So please be sure that you are using the notes that we have done. You are using the graphing calculator. You are thinking about an appropriate domain. You're not going to go negative as far as time goes. You're not going to go negative as far as height goes. So you do want to keep things in that context. Okay? And then read whatever the problem is telling you. That's how we can describe things like, oh, at 10 seconds, the rocket is back on the ground. That's context of the problem. So make sure you're using all of that to help you. Ask me for help if you need it. And we are going to start prepping for our Chapter 11 quiz now. All right, let me know what you need and I will be with you. Thanks, Algebra. See you soon. Bye.